Hey, Dr. Clark coming at you here, and in this video we're going to start to learn about line integrals. Let's get started. So before we can do line integrals, we need to do a quick review of arc length. So you might remember that arc length for a curve is given by this function here, or, well, rather this integral. And if you want to remember where that sort of comes from, if you have a graph of some function f of x, then you could chop that graph up into little lengths. Maybe you'd call those dx, and there would be a certain change in x there and a certain change in y. And it turns out that the slope, the derivative, f prime, is equal to dy over dx, at least instantaneously. And therefore, if you want to know, for example, what that length is right there, because an arc length is going to measure that length, that we might even call ds. Well, you would say ds squared should equal dx squared plus dy squared. And therefore, ds squared should equal dx squared times 1 plus dy over dx squared. If we just factor out a dx squared there, and then square rooting, we could find that ds is equal to the square root of 1 plus dy dx squared. Well, that's f prime squared, and then dx on the outside. So really what we're doing is we're chopping up the interval into a bunch of little bite-sized pieces, and for each little bite-sized piece, we're measuring the length of that ds there, and then we're going to add up all those little patches of ds. Well, that's what an integral does. It adds up all these little ds's. So you might even call this thing right here, that whole thing, ds. Okay? Now, if you were doing this in parametric equations, then you might have some curve moving around like so. Well, between any 2 points, you would have a certain amount of length. There'd still be a ds there, but it would turn out that that ds would be this times dt. So dt was a change in time. This is really the velocity. It's really, if this is your velocity vector v, well, the velocity vector v would be given by x prime comma y prime, right? Velocity would be the derivative, and the length of that vector would be the square root of the sum of the components squared, which is what we have here. So you can see that these arc length integrals are really important to understanding line integrals. It's essentially just building on this idea. And so what we want to do is think about how could we use arc length to think about, say, the mass of a wire or something like that. So maybe you've got some wire, and that wire is thicker in some places and thinner in other places, and you want to know the total mass of that wire or something like that. Well, what you can do is you can think of a function, you know, we'll just say f of x, I guess. Well, maybe we'll just say f. And that function maybe gives you the mass of a particular little bit of wire. So, you know, almost like a density. Well, then you could add up all these densities at all these different points along the wire, and you could get the total mass of the wire. And that's the idea we want to build on here. And so we're going to call this a line integral. We're going to call it a scalar line integral. And the setup is going to be a curve C in space. So C is some curve, possibly even in 3 dimensions, given by parametric equations x of t, y of t, z of t for t's between a and b. Okay? If you want it to be a 2-dimensional curve, then just set z equal to 0. And you can think of that path then in space as a vector valued function. R of t, it tells you where you are. So at a given time t, it tells you where you are. You're right here at r of t at that point. And the vector x of t, y of t, z of t points to where you are. And then the arc length formula is essentially just made in terms of this r of t. And what I want you to notice then is r prime of t, the derivative of r, would be x prime, y prime, z prime. And then the length of r prime of t would be the square root of x prime squared plus y prime squared plus z prime squared. So essentially, the length of your position vector, well, that's where, not the length of the position vector, but the length of the velocity vector that comes from the derivative of the position vector, is really going to give us the arc length in a sense, because it'll tell us the velocity at each point. So here, if the velocity is there, it's telling us I'm going a certain speed. And that's where the line integral comes from. So what we're going to do is we're essentially just going to put a function here that gives us the thing we're integrating. And this here is really our ds. So that derivative of the position vector, or the derivative of the position vector is the velocity, the magnitude of the velocity is the speed, speed times time is length. So this is a little package of length, which you call ds. And we're going to take that little ds of length and take it times the thickness of the wire, and that's going to give us, say, a mass, right? And so if the wire's thinner here and then thicker here, you've got thicker densities here, smaller densities there, thicker densities there, times these little packets of arc length. And the integral will add up all those, okay? And this doesn't have to be mass, of course. It could be any function. Okay, and then if you want to know, well, what is r prime of t? Well, it's really just the square root of x prime squared plus y prime squared plus z prime squared dt, and this could be in 2 dimensions as well. If you just set z equal to 0, now you've got a 2-dimensional curve. So really, when we say a line integral, what we're saying is we've got some curve in space and some function we want to integrate along that curve with respect to ds, which is the natural length measure on the curve. Okay? The way you do that is you put the locations on the curve into the function, right? We want to evaluate the function along the curve here and take that times ds. Well, where do you get ds? Well, that's coming from the velocity, the length of the velocity vector. All right. So that's the main idea for what is a scalar line integral. In the next video, I'll do a couple example problems, and you'll see how to work out some problems. So we'll see you in the next video.